All right, so I know it's been a while, but I have finally finished running the RNN models for the Bird Song Classifier project. And today I'm going to go over the RNN models. So for the RNN models, I ran both LSTM and gated recurrent unit models. So for the LSTM, it stands for long-term short-term memory. And here's a Wikipedia page that also shows the architecture of the LSTM model, a typical LSTM model. And then for the GRU RNN, which is the gated recurrent unit model, this is also the Wikipedia page that shows the architecture. So the GRU RNN model is like a LSTM model, but with a gated mechanism. And I am not going to code from scratch today. For today's video, I'm just going to go over the code that I had already run for LSTM and GRU RNN. So without further ado, here is my GitHub page. We can see the LSTM and GRU RNN models under the RNN folder. So I'm going to first go over the LSTM model. Similar to other models I've already ran for feedforward and CNN models. So this is the same model that the same notebook that I copied from the CNN model. And we're using the 8-second audio features and without average pooling. And for the LSTM model, I'm actually not going to use continents, so I'm using only audio features. And I'm just going to scroll down to the part where the model is. Similar to previously, we load all the features and the labels and the model and the weights for the sample weights. Essentially, the audios with the higher quality, hence the higher rating, will be given a little bit more weights during training. And to create the LSTM model is really quite simple. Here I'm again using the TensorFlow for creating the model. Differ from the CNN model for LSTM, I am actually using the sequential architecture instead of the functional API architecture because the RN models are sequential in nature. So here's the function for building the LSTM model. We first passing the audio features to the input layer, and then I create the sequential model by calling Keras model sequential, and then I add the LSTM layer, which takes in the number of LSTM nodes into as a parameter, and then I add batch normalization and dropout layers, both of which are used to prevent overfitting. And then for the hidden dense layers, I have the default have 3 layers, each with 128, 64, and 32 nodes, respectively, each activated with ReLU with the regularization L2 with strength of 0.01. And each hidden layer is followed by a dropout layer of dropout strength of 0.2. Again, the regularization and dropout are used to prevent overfitting. And then the model is finished with a final dense layer with the activation of softmax. Remember, we have 3 classes, so the final dense layer has 3 units. And then I compile the model and by using the Atom optimizer, similar to all the other models we've ran. And for the loss, I'm using sparse categorical cross entropy. And for metrics, I'm using accuracy. And similarly for the weighted metrics, I'm also using accuracy. Again, the weighted metrics is referring to the sample weights based on the rating. To train the model, I first create the audio features by concatenating each of the audio features that I want to use. Similar to the previous models I've ran, I experiment with the different combinations of audio features for training and validation. And then I fit the model by first specifying a callback with patience of 20 and start from epoch 50 with the early stopping callback and to restore the best weights. So when we build the model, after we build the model, we can fit the model. We can see here that I pass in the learning rate, the LSTM layer size, and the hidden layer size, and the dropout strength. and I trained it for 100 epoch. Again, this will stop most likely before 100 epoch because of the callback technique. And I'm passing in the audio features and the sample weights. And here is where I get the best epoch, and then I visualize the results. Here is the model summary as it's being compiled. We can see that we start with a LSTM layer of 256 nodes, followed by a batch normalization and a dropout layer, and then followed by 3 dense layers, each followed by a dropout, with a final dense layer of 3 units. And here is the training progression. I'm just going to scroll down to the bottom to look at the training progression graph. And here is the plot of the model. This is essentially conveying the same information as the summary, except the summary also tells us the number of trainable and non-trainable parameters, as can be seen here. So after experimenting with the different features, I'm just going to scroll down to the bottom where we have the summary. So the results from all the models, we can see that the model with MFCC and spectral centroid had the best performance with a 97 training accuracy and 91 validation accuracy. So for this model, I am going to also look at so here is the training progression graph and the classification report and the confusion matrix. We can see that the progression actually has quite a bit of zigzag, especially at the beginning of training. At least for the first almost 30 epoch, the model is seem to be struggling from one epoch to another. But then the zigzag starts to become less after the around 30 epoch. And we can see the training and validation are kind of converging. By looking at the classification report and the confusion matrix, we can see that the performance is actually comparable to that of the 1D CNN. Note here that LSTM actually is quite computationally expensive. So for training the model, I actually used a T4 GPU to train the models. If you don't use a T4 GPU, it will take quite a bit of time. The Google Colab free version comes with a T4 GPU that you can use. And now I'm going to move on to the GRU-RNN model. So again, the GRU-RNN model is similar to LSTM, but with a gated mechanism. And the notebook is similar to that of LSTM. The only difference is that for the GRU-RNN, I'm going to scroll down to the part where the model was defined. We replaced the LSTM layer with a GRU layer. So that's literally the only difference between LSTM and GRU-RNN when implemented with the TensorFlow. You can see it's actually quite easy. And similarly, I'm using only the audio features. For the GRU-RNN, I use the same hyperparameter as LSTM with the same learning rate, same initial node size, the hidden layer size, and the dropout strength. And here's the training progression. And I'm just going to scroll down to the bottom. We can see that with the GRU-RNN model, the best performing model is the MFCC plus RMS plus spectral centroid, where we had 99% training accuracy and 93% validation accuracy. Actually, for the MFCC plus RMS, we also had 99% training accuracy and 93% validation accuracy, at least for the trainings we ran here. So I'm going to discuss the MFCC plus RMS version, since it seems like spectral centroid here did not really add value. So here is the training progression graph for the GRU-RNN model with MFCC and RMS as the audio features. We can see that the zigzag is definitely less prominent than the training progression graph for the LSTM model. And the model is converging a little bit faster. Here, the model converged at, I could probably stop it at around 20 or 30 epoch. but because of the callback technique I used, it stopped at around 60. So the model could be just a little bit overfitted than ideal, but I'm not overly worried about that. And then we can look at the training and validation classification report and confusion matrix. We can see that this is definitely performing better than LSTM and even performing better than the 1D CNN. One thing to note is that, again, since it's an RNN model, it is computationally expensive. So I used the 84 GPU to train the models. So that's it for this video. I hope you found it useful. Again, all of the code you can find on my GitHub page. And for the analysis I did for the RNN models, you can find on my website. Thank you.